Hi everyone, and welcome to this new video about control systems, and we continue with the subject of gain margin and phase margin. In this example, we will discuss a fourth order system, which is shown here. This is the plant, which has 4 poles and 1 0, which is a little bit different than the previous example, a little bit challenging. And we have the closed loop system as shown here, and we have the proportional controller, the gain, which is given as K. So we have the feedback control, again, unity gain, feedback. Now the questions are the following. A, calculate the value of this proportional controller gain K such that the closed loop system has a gain margin of at least 12 dB. So this is a little bit different than the previous example. Then we started with the phase margin. We start here with the gain margin first. The question B is calculate the phase margin for the calculated value of K in question A. So we need first the value of K from question A, and then we will use that to calculate the associated phase margin. Okay, let's start with the example. How do we start? As we did in the previous examples, in the previous videos, we start first with determining the loop gain. So let me write it down, the loop gain. The loop gain, which is denoted here as L of S. Which is, of course, if you look at this configuration, loop gain is actually you start at one point and you come back at the same point. You make one full circle. So what we have is the gain and the plant and unity gain path. So it's actually K times the G, the plant, times 1. So it's actually K times the plant. So K times G. So what we have is K times the expression of the plant. So if you do that, you will get 100 times K times S plus 2, and then divided by the poles S plus 1, S plus 4, and then S plus 5, and S plus 6. Okay, what we need to do, and what we also did in the previous examples, we need to transfer this in the j omega domain. So what we have is set S equal to j omega. That we can do because we are working actually in a sinusoidal system, so we're working with pure sine wave analysis. So what we have is then the following. Your loop gain will transform in the j omega domain as follows. Only what you change is the S. So where you see an S, you replace it by j omega. That's actually the whole business. So 100K times j omega plus 2, and then divided by j omega plus 1, so j omega plus 4, and then j omega plus 5, and the final one is the j omega plus 6. Okay, as we did in the previous examples, let's determine also here the gain expression and the phase expression for the loop gain here. So let me write it down. So the gain and the phase. So let me do it in red this time. So the gain and also the phase. We will need this, of course, in the further analysis. So if I now continue with black, what you have, of course, the absolute value of your loop transfer function of loop gain is, of course, you look at the numerator and denominator, and you will, of course, take the length of this one. This one is, of course, 100K times the square root of omega squared plus 2 squared. This is, again, the familiar analysis we did in phases and complex numbers videos. So what we have is 100K and then square root of omega squared plus 2 squared. That is actually for the numerator. For the denominator, we have 4 terms, exact the same procedure. Square root of this, omega squared plus 1 squared, times square root of omega squared plus 4 squared, and then times omega squared plus 5 squared, square root of that, and then square root of omega squared plus 6 squared. So if I write it down, I will make a template. We will get actually the following. So the square root, square root, square root, and then square root. So you will get actually 4 square roots, and then omega squared, and then 1 squared, which of course just 1, and then omega squared plus 4 squared, and then omega squared plus 5 squared, and then omega squared plus 6 squared. All right. So the next step is the phase. Now, the phase expression, you will look at this expression again for your loop transfer function. You will look at the numerator phase contribution and the denominator phase contribution. So the contribution of the numerator is positive and the contribution of the denominator is negative. So what you have, if I move a little bit to the right side and I see the loop transfer function and the phase expression here, so I will just divide this clearly. So what I have is the phase expression is the arctangent, which is just the one term from the numerator, is omega divided by 2. And the minus, the first term from the denominator, is the arctangent omega divided by 1. Of course, it's just omega. And then minus arctangent omega divided by the 4. Let me move a little bit more to the right side, or a little bit zoom out. So what we have is a minus sign and an arctangent omega divided by 5, and the final one is the minus arctangent omega divided by 6. So this is actually our expression for the phase, and this is actually our expression for the gain. Okay, what do we do next? If I look at question A, I will zoom in a little bit. So if I look at question A, this actually are asking us the gain margin of at least 12 dB. So we need to calculate the value of K such that we have a gain margin of at least 12 dB. So I will now move to question A, which is actually, let me write it down, required is the gain margin is larger or equal to 12 dB. We can of course convert this to factors. So that means actually the following. If I have the loop transfer function L, so if I have the loop transfer function L, and if I take the magnitude of that, so that's actually this expression, the gain, and I look at the gain margin frequency, that value must be equal to minus 12 dB. Why? Okay. What is the gain margin definition? The gain margin is saying the following. At the gain margin frequency, I need a distance from the 0 dB of 12 dB in this example. So if I have, for example, a gain margin of 20 dB, then that must be minus 20. If I want, for example, 30 dB, then that must be minus 30 dB. So I need a distance, or I need a safety or headroom of a specific gain, and this is actually what I require. So this is now 12 dB, so I will need a gain, which is of course just attenuation of minus 12 dB, so I can add another 12 dB, so I can come to 0 dB. That's actually the whole idea behind this issue. So what we have is, of course, in dB expressed in this, and if I now convert this in just factors, so I will have 10 to the power minus 12 divided by 20. So it is actually the conversion from the factors to dB expression. So I can, let me write it down in a different form. So I can also have the loop gain at that frequency, omega gain margin, but then of course just as a factor, that vector. So it will be of course 10 to the power minus 12 divided by 20. And this is very close to 0.251. Okay. What is the following step? The frequency, the omega GM, is the frequency. So the omega GM is the frequency. Let me write it down. It's a frequency where the phase of the loop gain, so of L j omega, is minus 180 degrees. That's also the definition of the gain margin. So I can use the expression for the, or the formula for the phase, which is of course shown here, which is a very long formula. I can use this formula and equate this to minus 180 degrees. And I can know, I can then calculate the value of that omega, and which is then omega gm. Then I can use that and calculate and use that in the expression for the gain, and I can then calculate k. So the first step is calculate the value of omega gm for, of course, this phase, which is just the definition of the gain margin, and then use that omega value in the gain expression of the loop transfer function, and then calculate the value of k, because I need then, for that specific frequency, I need a gain of 0.251. So first, let's start with the phase expression. So let's move on with the phase. So let's do that. What is the phase? I need a phase of minus 180 degrees. If I just take this completely and equate this to this 100 minus 180 degrees, you can do the math for yourself, which is not really that difficult. You will get the omega is equal to very close to 7.83 radians per second, which is now defined as omega gm, which is just the gain margin frequency. So I will underscore this. Okay, now I will now use this value in the expression of the loop transfer function magnitude, and then calculate the required value for k, such that I can get a gain of 0.251. So the next step is, let me zoom in and continue here. So the next step is loop transfer function at that specific frequency is 0.251. I already said that. Now I can of course say that's 100k and then square root of 7.83 squared plus 2 squared. That's the numerator. Let me make some room here, and then square root, square root, square root, and then square root, and that must be of course equal to 0.251. Now if I now substitute the values, I will get, of course, this 7.83 squared plus 1 squared, and then 7.83 squared plus 4 squared, and then 7.83 squared plus 5 squared, and the final one 7.83 squared plus 6 squared. Again, you can do the math here using a solver. It's not really that difficult. Actually, this is just a very simple for expression, which is a linear function. What you get is a value for k, which is now k is equal to 1.98, very close to 1.98. All right, I will get this. What's now the next step? Now, I have now calculated actually for question A what the required value is for my gain margin. So this is the gain for a gain margin of 12 dB. Let me write it down a little bit clear, so it's 12 dB. I need that gain. If I of course increase it, for example, make it 3 or 4, 5, 6, of course then your gain margin will decrease. If you lower this, for example, make it 1 or 0.6 or 0.4, you will increase your gain margin. That means actually this is just the maximum value for your gain of your controller in order to get that at least 12 dB. So don't go above this value. If you of course want to have some safety, you can of course make it 1.9 or 1.7. That's actually a design consideration. Now, let's move to the question B. What's the question B? Calculate the phase margin for the calculated value of k in question A. So they're actually the following. You have now your loop transfer function, which is now has a known value of k, which is the controller gain. And for that new loop transfer function, I will of course calculate the phase margin. So my loop transfer function, the new one, of course with the value of k, is 100 times that 1.98, which is shown here. It will be of course 198 times this and divided by the 4 poles. So what I have is the following. I will have 198 times j omega plus 2 divided by j omega plus 1 times j omega plus 4 times j omega plus 5 times j omega plus 6. That's actually my loop transfer function for calculation of the phase margin. What was the required situation for the phase margin? What was the definition? You look actually to your gain of your loop transfer function, which is 1, and then calculate what the phase is at that frequency. So what you do is first, what is, or at what frequency do I get a value of 1? So I need to actually do this. So let me continue with black. I will have to do 198 and then square root of omega squared plus 2 squared. Again, a little bit similar analysis with square roots, and square roots, and square roots. And I will, of course, this time equate to that 1, which is 0 dB, which is omega squared plus 1 squared, omega squared plus 4 squared, omega squared plus 5 squared, and then omega squared plus 6 squared. Now, you can do the math here. It is not really that difficult. Just substitute that in a solver or another program. You will get very close to 3.42 radians per second, which is now defined as the omega PM, which is just the phase margin frequency. So I will underscore this, which is the phase margin frequency. I need that. Why? For the definition of the phase margin, I say the following. So let me continue with blue. Phase margin is 180 degrees plus the phase, which is of course found using the expression of the phase what we get from the loop transfer function at this frequency. Now, if I now substitute the omega PM in the expression for the phase, which was of course determined already here. So if I now use this formula and substitute there 3.42. You can do the math for yourself. It's not really that difficult, so I will just write it down. If you do the math here for yourself, you will get very close to minus 119 degrees, so 119, minus 119. Now, if I now substitute that in the expression here, I will get a phase margin of 180 minus 119. It will result in 61 degrees as a phase margin. So in summary, let me write it down. So in summary, you will require a K of 1.98, which is of course the maximum. And then you will get a gain margin of 12 dB, and your phase margin associated with that gain will be 61 degrees. This is actually the summary of the whole analysis. Of course, if you increase this, you will lower your gain margin. If you decrease this, you will increase your gain margin. So that is just the maximum. So this is the maximum value. So let me write it down. So the maximum controller gain, or maximum gain allowed. All right, that's actually for this example. Of course, we will continue with different examples and different topics and control system and other issues. So keep in touch and don't forget to like and share. And see you next time. And if you have, of course, questions or comments or want to discuss something, just leave it in the comment section. I will try to answer them as soon as possible. Thank you very much and have a nice day.